All right, let's talk about something that sounds like it's pulled straight from science fiction, putting these massive AI data centers into orbit around Earth. Now, it might sound pretty wild, but this whole idea is actually being driven by some very, very real problems we're starting to face right here on the ground.
So the first question that probably pops into your head is, why, right? Why on earth would we go through all the trouble and the incredible expense of launching this super complex, super heavy hardware into orbit just to run AI models? Well, the answer really boils down to the two things that AI absolutely craves more than anything else: power and cooling.
You see, down here on Earth, AI is starting to hit a wall. I mean, a literal physical wall. Our data centers are totally limited by the electrical grid, and they guzzle unbelievable amounts of fresh water just to keep from overheating. But in orbit? Well, up there, you have near-constant, totally unfiltered solar energy. And for cooling, you've got the infinite freezing cold vacuum of space. On paper, it's a perfect match, right?
Of course, if it were really that simple, we'd probably already be doing it. That beautiful, elegant solution of space is cold kinda hides a couple of absolutely massive engineering challenges. It's not nearly as simple as just, opening a window to cool things off. So, what's the catch? Well, it really all boils down to two huge fundamental problems that are completely tangled up with each other. First, you have to somehow get rid of all the waste heat that those incredibly powerful AI chips are generating. And second, you have to protect those very same, very sensitive chips from the constant bombardment of cosmic radiation.
And this is the absolute key. The source material really hammers this home. You cannot solve one of these problems without directly affecting the other one. They are completely inextricably linked. Every single engineering decision you make about heat has a direct and often negative consequence for radiation, and vice versa.
And here's where you can really see that conflict play out. To get rid of heat, you need these huge, heavy cooling systems called radiators. But to protect your electronics from radiation, you need heavy shielding. Every single kilogram you use for a bigger radiator is a kilogram you can't use for shielding. And just to make it worse, running your chips hotter actually makes your cooling systems more efficient, but it can also make them way more vulnerable to radiation damage. It's a true engineer's nightmare.
So let's break that down. And we'll start with heat, because this isn't just a problem. The technical report actually calls it the primary bottleneck. It's the single biggest factor that will decide whether an orbital data center is even possible in the first place. Here on Earth, cooling is easy. You just use fans to blow air or pumps to move water. But in the total vacuum of space, you only have one option: radiative heat rejection. The hardware has to literally glow with heat, not visibly, but in the infrared spectrum, to beam that energy away into the void. The only ways to get better at it are to build a bigger radiating surface, or to get that surface a whole lot hotter. So just how big are we talking about here? Well, to cool just a single 100 kilowatt AI rack, which, by the way, isn't even that big by today's standards, you would need a radiator that's about 120 square meters. To put that in perspective, that's roughly the size of a tennis court's doubles playing area, all strapped to a single satellite. This is where the choice of materials becomes absolutely critical. You can see the trade-offs right here. You could go with something like aluminum, which is flight-proven, we know it works, but it's pretty heavy. Titanium can handle way higher temperatures, but look, it's even denser. The real holy grail here is these advanced materials like carbon-carbon composites, which are just unbelievably lightweight. And this right here, this shows you just how high the stakes are. By switching from a standard aluminum to an advanced carbon-carbon design for that tennis court-sized radiator, you could save up to 840 kilograms. That is a massive amount of weight on a spacecraft, and that's all mass you can now dedicate to that critical radiation shielding, or hey, even more AI chips. But, as if that wasn't hard enough, there's another invisible threat lurking up there. In low Earth orbit, you have these single, highly reactive atoms of oxygen that are just constantly slamming into the surfaces of your radiator. This atomic oxygen literally eats away at the special coatings you need to shed heat efficiently, degrading your entire cooling system over the life of the mission. Okay, so we've talked about the incredible challenge of getting the heat out. Now let's dive into the other half of this engineering nightmare. How do you survive the constant barrage of space radiation? How do you dodge these cosmic bullets?
The thing is, modern AI chips are just exquisitely vulnerable. A single high-energy particle can strike a memory cell and cause what's called a single event upset. That just flips a bit from a 0 to a 1, and suddenly your entire AI model's calculation is corrupted. Even worse is something called a latch-up, which can create a tiny short circuit that physically destroys the chip. And all the while, the total ionizing dose is building up, slowly poisoning the hardware until it just fails.
So,
How do you possibly defend against all this? Well, there's no single magic shield. Instead, engineers have to use this multi-layered strategy. You can use specially built tough-as-nails chips or add targeted physical shielding. You can design redundant circuits that literally vote on the right answer, or even create smarter software that can actually tolerate some errors. And finally, you can just pick safer orbits to fly in.
This really leads to two competing philosophies of protection. On one hand, you've got the fortress approach. You just try to make everything totally immune using these super expensive, kind of slow, but incredibly tough radiation-hardened chips. Then you've got the immune system approach. Use the fast commercial chips you want, and then build a clever system around them to manage and correct the errors that you know are going to happen.
So which one wins? Well, it turns out the hybrid approach is really the most practical path forward. The idea is you use a small, ultra-reliable rad-hard chip to act as the foreman, the brain that manages all the critical functions. And then, for the really heavy AI number crunching, you use big clusters of the fastest commercial chips you can find, and you protect them with all those layers, shielding, error correction, and really smart software.
Okay, so let's bring all of this together. We've seen these two monumental challenges, heat and radiation. So what does a viable, near-term solution actually look like when you synthesize all these different engineering ideas? For the thermal problem, the smartest plan is to start with what we know works. That means using those flight-proven aluminum radiators with really durable inorganic paint coatings. And here's the key trick. You run the whole system as hot as you possibly can, maybe 80 to 100 degrees Celsius, because that allows you to radiate heat away much more efficiently. And you use pumped fluid loops to get the heat from the chips out to those giant radiators.
And for the radiation problem, it is all about that defense-in-depth strategy. You use that hybrid hardware we just talked about with a tough little control chip and powerful commercial AI processors. But the real secret sauce is a heavy reliance on software and logic. Things like error-correcting codes, constant memory checks, and even AI models designed to be more resilient from the get-go. The goal here isn't to be invincible. It's to degrade gracefully, not fail catastrophically.
And that brings us to the most crucial takeaway of all. There is no silver bullet here. You can't just invent a perfect radiator or a perfect radiation shield and call it a day. Success depends entirely on creating an integrated system where the thermal design and the radiation solution are engineered together, hand in glove, right from the very beginning. Look, the engineering gauntlet is formidable. There is absolutely no question about that. But with this clear, integrated pathway forward, it raises a really fascinating final thought. We're so used to thinking of the cloud as this abstract, ethereal thing, but its physical constraints, power and cooling, are incredibly real. So could the next great leap in artificial intelligence actually be powered not from the ground, but from orbit?